Thanks. Hi, everyone. Happy to be here. Thank you, everyone, for coming. So today we're going to talk actually about two papers. I changed a bit the plan for today because I think it's a bit interesting to cover these two papers. The first one is called Vision Transformers Need Registers. It's a paper we published with my advisors a year and a half ago, approximately. It's about studying vision transformers, so we're going to discuss that a bit later in more detail. But basically what we find is that when we study the specific architecture, vision transformer is just a network architecture for vision, you can find something weird inside, some artifacts. We study those artifacts and we try to interpret what we're seeing and find a fix that we call registers to prevent them from happening. Now, I had a bit of a slide about me, but he introduced me, but very quickly. So my name is Timothée Darcet. PhD student. These are my advisors, but before that, I did a master's at ENS and at Polytechnique, which are French universities, and I work on self-supervised learning and on vision transformers. Today, we're going to cover both, one paper each. These are the papers I did during my thesis, and basically these are the two papers we're gonna discuss. Now, before we start discussing what vision transformers need registers, a bit of context. What is a vision transformer? Very simple. A vision transformer is one architecture to do vision tasks, often things like classification, for example, and it works very well. If you know transformers in NLP, it's very similar. The idea is that you've got an image, you got to cut it up into patches. You split it into patches, and then you pass all of these patches as tokens, so they are each a separate token to the transformer. To get the token value, you just flatten all the pixel values. Like if the patch is 16 by 16 pixels, with each pixel having 3 pixel values, RGB, then it gives 16 by 16 by 16, 768 dimensions. You add a special token that is a class token, CLS token. Why do we add this? This token is the one that is supposed to aggregate the global information about the image. When you do classification tasks, for example, how do you train this architecture? Well, you do this thing, and at the output on top of the CLS token, you add an MLP or linear layer, whatever classifier, and you train with classification loss. Something very simple. Now, something very specific you can do in transformers is attention maps. Attention maps is something we do in vision transformers in particular, which is looking at where is the CLS token looking at. What do I mean by that? In each block of the transformer, you have this self-attention layer. Self-attention layer, you see, will have some interaction between all the tokens, pairwise, the CLS token and the patch tokens. At the output, the CLS token will have attended gathered information from different tokens, the patches and the CLS. What you can do is look at these attention scores. How much attention was given by the CLS token to the patch tokens. In the same way that these patch tokens were an image originally, so you could reshape them, you can reshape these attention scores and obtain a heat map. This heat map is what we call the attention map of the CLS token to the patch tokens. Why is it interesting? Because you must understand that in transformers, this attention layer is the only way to have any sort of communication between tokens. And as we were seeing previously, like at the beginning of the transformer, like before the first layer, the CLS token does not have any information about the image. So if the CLS token is going to have classification information at the top, it must gather this information from the patches. At each layer is going to gather some information, and this is really the whole flow of information from the patches to the CLS token. And that's interesting, because a lot of people work in like machine learning in some things like interpretability, attribution maps. You have a lot of work on CNNs about things like GradCam, for example, which is a method to try to localize where does a given classification come from. This is a free interpretability tool, like built into the model. There's no guarantee that it's actually a super good interpretability tool, but it's still interesting to show it. And so as soon as vision transformers were published, people have started looking at those. They look at those and they look bad. They look weird, more specifically. Like these are for a lot of models that are taken off the shelf, like just downloaded from internet. I plot the attention maps on a few images. Here, the highest attention values are in yellow, and blue means basically zero attention given there. And as you can see, it's a bit surprising. Like basically, you would expect that this first thing ViT, which is a classification model, to classify this image as a cat. 99% certain it classifies it correctly. To classify this image as a cat, you would expect the TLS token to look at the cat. Instead, it's looking at two patches, seemingly like random, in the background on the wall. Makes no sense. You can see that it's basically the case for all models, except a bit for Dino. Dino has nice attention maps. Dino is a self-supervised learning model, which means it was trained without any label. It was actually a very important thing in the original Dino paper, these attention maps. As you can see, it is actually attending to the beetle here, to the donuts here. So these are nice attention maps, cool. But then Dino V2, when we did that, it looks bad again. So there's really some weird things happening here, and the whole question basically sums up to what is going on. So what is going on? And to do that, we're going to try and study the artifacts. First thing, I want to kind of detect them. I want to have a criterion to say, okay, this patch, I consider it an artifact. And we just probe around the model, and we see very quickly that there's something very clear. These tokens, the artifacts, have very high norm. So if you consider the L2 norm, just normal, the norm value of the token, it's just much higher than all the other tokens here. It's very yellow, like higher than the rest of the tokens. In Dino, you would not have these outliers. Actually, you can plot a histogram to see the outliers. And what you see is that in Dino, the histogram is just one lump. In Dino V2, we've got one lump and then another lump at very high norm, around 500, which is very high compared to the rest. Note that this histogram is a bit misleading because of the log scale, but basically these are very few outliers. There's about 2% of tokens which are in this lump at high norm. But there's a very clear divide between the two. What you can do is say, okay, I'm going to put a threshold at, let's say, 150. Tokens that have more than 150 norm, these are my artifacts. I consider these are my artifacts, and I'm going to try to compute some statistics about them to understand them better. First thing we can think, when do they appear? In terms of the layers in the transformer, for example. Because at the input, you have no artifact. At the input, these are just pixel values following a given distribution that is absolutely not outlier probe. But around the middle, like this, you've got this offshoot of the distribution that just goes up to very high, up to 500. This is again a log scale, up to 500 norm. So super high norms just offshooting around the middle of the model. Right, but well, that does not tell us that much. In the training, you can look, and it's interesting because at the beginning, you don't have anything that weird. It's just after a while in the training, you've got again an offshoot of the distribution that stays at super high norm. It means probably that if we train for a very short time, we don't have any outliers. So it's something that emerges during the training. You need to train long for that. Last thing is, what about model size? You could train multiple models with different architectures. These are vision transformer architectures, tiny, small, base, large, huge, and giant. Basically, they're just bigger and bigger from left to right. And as you can see, it's just these outliers appear very suddenly when going from base to large. It's a very sudden jump, but it means that you need to have a given model size. It's only after a certain model size that these outliers appear. These are interesting clues, but they don't really explain anything. So let's get down to something else. Where do they appear? As I was saying earlier, in this image of the cat, these outliers appear on the wall. So it seems to be in kind of background areas. It's kind of the same here. It's in the sky. So background areas, how can we quantify that? Let's try to see if we can measure that and show in terms of numbers that it happens. What we can measure is it appearing on patches that are similar to the neighbors? Let me explain. You forward an image with your vision transformer, you get your patch tokens. Compute the norm of all those patch tokens, and you see that a few are outliers, a few are much higher norm than the others. So you mark these patch tokens, you mark these locations, and you say, these are my artifacts. Then you go back to the image and you look at, okay, what was there in the image where these artifacts appeared? You take this patch that was the location at which they appear, and you compare it in terms of cosine similarity to the 4 neighboring patches. And what you see is that if you plot the distribution of cosine similarity, for artifact patches, you've got a ton of those cosine similarities that are at 1, meaning basically the same. Artifact patches appear on patches that are basically the same as their neighbors. This is not the case for normal patches. If we plot the distribution in blue, that is a control group, basically the distribution of normal cosine similarity for normal patches, it's much more flat. It's much more spread out. So we've got this very interesting spike. Means it happens on patches that are redundant to their neighbors, meaning they have the same information as the neighbors. So the model could probably like discard these patches and not really suffer from it, because it's basically the same patch as a neighbor. Like if you have 50 patches of sky, at some point you can discard a few of them and the model still knows that it's sky around here. But that's a bit getting ahead of ourselves. Let's try and test for that. Is the model discarding this information? For that, we're going to probe. What is probing? We're going to take the output patches, the tokens output by the model, and we're going to we're going to train a linear layer or any kind of model, but in our case, the simplest model, linear layer. We're going to train it to recover a given type of information from the patches. And what information are we looking for? Well, in the patch tokens, in the vision transformer, there are 2 informations at the beginning. The pixel values. If you remember correctly, these were the patch tokens initially are just pixel values flattened. And 2, the position. There is a positional encoding that is added to the patch tokens. And so these 2 things are very well encoded and recoverable at the beginning of the transformer. Question is it still there at the end? Did the model just discard this information? And so for that, you look at these values, you train linear probe, and you see that if we compare between the outliers and the normal patches, the outliers have much less positional information, lower accuracy, higher average distance, but much less also, pixel information in terms of reconstruction. The reconstruction is much more noisy. It's much further away from the actual pixels. So the model did discard the local information that was encoded into it at the beginning of the transformer. That's super weird. There's no incentive for the model to do that. The model needs this information to do classification perfectly. There's no good reason for the model to discard that. So let's think about what the model was trying to do. Maybe it was trying to make space for something else. Maybe it was not explicitly discarding it, but overwriting it with something else. What we could look for is global information. That is basically the opposite of local information. Information about the whole image. Information about the whole image means, for example, information about the class of the whole image in classification datasets. So we take this ton of classification datasets, ImageNet, Places, whatever. In all of these datasets, we have the class of the image, meaning a category. And so we can train, again, a linear probe, but instead of training it to recover these things, we train it to recover the class of the whole image. See how much global information is encoded in the patch token. And we compare that for outlier tokens. When we pick an outlier token that has a lot of global information, for normal tokens, and for the CLS token. The CLS token is like the top line. It's the token that is supposed to encode the global information, to aggregate it. So of course, it's going to have a ton of that. As you can see, basically the outlier tokens are not as good as the CLS token on this task, but are still much better than the normal tokens. On some benchmarks, it's not that clear, but then you look at, for example, aircraft, and it goes from 17 to 79. A huge gap between the normal patch tokens and the outlier patch tokens. Again here, Cub 1884. These tokens aggregate global information. This is very interesting behavior, and we've got enough data now to try and formulate a hypothesis. Let's try to sum up everything we've seen so far. Large, sufficiently trained models. As we saw, it does not appear in every model. Some models, after a certain point, start recognizing useless tokens, redundant, that they don't need, discarding the local information and overwriting it with global information. That's a very interesting thing. Very interesting. Again, it's a hypothesis. We saw some clues, but what we're doing here really is like model psychology, you know, and when you're doing that, it's really hand wavy. We have clues, but we don't have like proofs. Don't believe me too much. But it's good enough. It's good enough of a hypothesis for now to just try and design a fix. See if we can fix this behavior. But before we get onto that, you might say, wait, why do we need a fix? This behavior is weird. This behavior is clearly weird for a human person that sees it, but who am I to say how the model should behave? If the optimizer found this thing, maybe it's the way to minimize the loss. Who knows? Well, two things. First thing is interpretability. As I was saying, it's nice to get something like the model says dog on this image. Well, the attention map does not look like that, but rather like that. This is a very nice attention map that shows where does the information come from that allows us to say dog. Second thing is feature maps are useful sometimes for downstream tasks. And the thing is, these artifacts are not only in the attention map, but also in the feature maps. This is a very small PCA, like the first principal component of the features outputted by a model on this image. As you can see, you get these artifacts are very visible. They are just very much visible in the features. And so that means that if you try to do something downstream, like segmentation, monocular depth estimation, these kind of things, you might get noise. This is not perfect. With the fix that I'll present in a second, the feature maps are much better. Now, what does the fix look like? The fix is very simple. What I say is, whatever you do, sure, do your thing, but don't do it in my patch tokens. Like I like them, I need them, I want them for my downstream tasks, so do it somewhere else. I give you some tokens if you want. I have some budget, a few other tokens, like 1, 4, who knows. But these behavior, just do it there, please. But the crucial point is we don't encourage it. We just add these tokens and let the model do whatever it wants. But what's interesting is that if you just do that, this simple thing of concatenating a few tokens into the sequence, the artifacts disappear entirely. The artifacts disappear entirely, so the model learns to use those tokens for the purpose it was using the weird patch tokens before. Like, it's interesting that it worked. In a sense, it's not that surprising to me because before that, it had to learn to do this weird behavior in the patch tokens. But the patch tokens already had some information, so it had to learn to write it. It's really not incentivized. But here, those tokens I added, those are really clean slates. They have no specific value at the beginning. It's just learnable tokens. And so when you add them, you get clean attention maps. You get also much better scores on some benchmarks. Now, these are not huge increases. Like, let's be honest, 84.4, you go to 84.8. It's not game changer, but these are quite competitive benchmarks, so it's significant. It's in particularly interesting in dense tasks, so segmentation and depths. As you can see, just going from 0 to 1 register makes a big difference, and that is visible here. You just have clean feature maps. It's much better. Something you can ask though is, all of this is Dino V2. It's one model. Does it work on other models, other training paradigms? And yes, we add these registers to also clip models or date models, which are classification models. So basically, self-supervised, text-supervised, and a label like classification-supervised models. 3 very different learning paradigms. And every time the distribution of token norms goes from by model like this, from having outliers to having no outliers. If you look at the attention maps, it's just much cleaner and very nice, and that's good. Now, I think that's all, because I think I removed the last slide. But yeah, if you have any questions, I'll go on to the next paper, and we'll discuss everything at the end. Yeah, remove the last slide. I'm going to drink a bit. So that you can breathe too, because we are changing topic. Let's get on to the second paper. Second paper is quite different. The first paper was very exploratory, it's like curiosity driven. There was no real goal of what we're doing. We just saw something weird and tried to understand it. Here there's a goal. The goal is self-supervised learning of representations. What does it mean? So what is self-supervised learning first? You probably, if you are into AI, a little bit know about supervised learning, which is basically when you have data and labels, and unsupervised learning, which is when you only have data, no labels. Self-supervised learning is a marketing term for unsupervised learning at the first order. It's slightly different, but honestly, you can consider it like this, and it's very fine to me. We are doing unsupervised learning. We're gonna have images, no labels, and we're gonna want to train something on these images. Now, why would we want to do that? The thing is representation learning. Representation learning is the idea of given an image, convert it to a vector. For example, you've got this nice image of our Lord, and you convert it to a vector. The thing is, when you have that, it's very nice. Why? Because vectors are really well behaved. An image is something complicated. You don't really know how to manipulate it. A vector, we know very well how to do stuff on vectors, like classification, you've got logistic regression. Clustering, you've got k-means. Like, you've got all these classical algorithms which are very cleanly defined and also very cleanly studied on vectors. Once you have vectors, you can do everything you want super easily. But of course, the question is, once you have good vectors, like that really represent the information in the image, where everything has the right properties to do linear classification and these kind of things. So it's hard to get the vectors to train this model, but that's what we're going to try to do. Now, and the first thing I want to start talking about is the fact that it works to some extent. Like, this is a nice, interesting starting point to make sure we don't go into a useless field. Self-supervised learning of representations works. You've got, so not everywhere, like it's, on a lot of things it's good, but just as good as like text supervised learning. But there are some domains where you cannot do text supervised learning or label supervised. For example, there are some domains where you just don't have much annotations. Medical data, for example, it's a very good example. You can have annotations. You can pay an annotator, like in every domain. But if you pay an annotator, it's a doctor. He's going to charge you like $1,000 per hour, and you will have 3 annotations, and you will be ruined. So these annotation scarce domains really care about trying to learn unsupervisedly without labels. You've got all of these projects, like these are really nice applications of DynoV2, which is a self-supervised approach. DynoV2 is not the only one that works, but it's the one I know well. But this is on chest X-ray, this is on satellite imagery, this is on histopathology. Apparently, we've got a reading group series on histopathology, so maybe we will discuss this paper, I don't know. And this is on rare plants. Yeah, those are really nice applications. A second thing that is maybe a bit more subtle is there's some type of understanding that, for now, emerges pretty well in self-supervised learning and not really well in other types of learning. The local and geometric understanding. What do I mean? For example, depth estimation, monocular depth. This is extracted from a paper called Depth Anything V2. Depth Anything V2 is basically a model. You give it an image and it predicts what is the monocular depth, meaning the distance to the object at each point in the image. And as you can see, it's very smooth, it looks very precise. It's even good on like these glass objects, which are very hard to predict. Depth Anything V2, as well as Depth Anything V1 and a lot of other models there, is based on DynoV2 self-supervised learning. Like, this pre-training helps a lot in these areas. You've got also things like point tracking here, Dyno Tracker. This is an interesting one. When you have good feature maps, you can distill it into an equivalent of a NERF, but a neural feature field. And this is like a 3D space of features. Won't detail it, but it's cool. So you've got these things that work. That's really nice. But the question is, how do we go further? Especially DynoV2, the one I'm presenting, and that's basically the one that's very good right now. DynoV2 is super complex, in my opinion. It's debatable, but in my opinion, it's really weird. This is a plot from one of the papers DynoV2 is based on. You've got these different losses. DynoV2 has these 2 losses plus a third one. It's a bit complex. Does not scale super well. might seem weird because DynoV2 is a big model compared to other models, but it was hard to scale it to 1 billion parameters. And going further is also hard. We'd like to have something that scales seamlessly. When you talk about, for example, language models, like, it's not easy to scale. Of course, you have the engineering challenges, and you've got to find the right recipe. But usually, it's more seamless than DynoV2. DynoV2 also has noisy feature maps. We've discussed before the feature maps of different models, especially DynoV2. We've fixed the specific artifacts that I was showing you. Now, the thing is, even if you fix these artifacts, there are some other artifacts. Like, basically, these are DynoV2 feature maps, DynoV2 plus reg, so one that is fixed with the registers. And you can see that it's got some kind of snow, like OTVs. It's not very clean. You would like to have something cleaner, so I would like to study DynoV2 and fix this. I would like to also make it scale better. But the thing is, it's so complex, it's really hard to do. So I'd like to do it to do something simpler that works as well as DynoV2. Not easy, but let's try to do that. To do that, let's look at the DynoV2 loss. DynoV2 is trained with these 3 losses. Dyno is pretty well studied. It's the original loss, was introduced by my research group, and we know it pretty well. We kind of understand what it's supposed to do and how it does it. We know it. Colio is something like a very small loss. Regularization does not really change the training dynamics too much. You add it, you remove it. Does not really change the training except you gain 1 point on some benchmarks. It's good, but it's like not really a main object of study. IBOT, though, is kind of a weird loss. We don't know it well, so let's look at it. IBOT was introduced 6 months after Dyno by a paper by Timothée Darcet from ByteDance. It was really good in terms of numbers. It was not very known, probably not well marketed or whatever, but it was really pretty good in terms of number, quite SOTA on the benchmarks it was targeting. In DynoV2, it was necessary, this IBOT loss. What do I mean by that? That if we don't use IBOT, we just don't get the same numbers. Especially look at segmentation on AD20K. You have a pretty big boost by using IBOT. We tried just removing it and getting the same numbers any other way. It just didn't really work. But, so this seems to mean that without IBOT, we don't get the same number. It seems to mean that IBOT has more signal than Dyno in some sense. Like, there's some residual signal that IBOT goes further than Dyno. But if you train just with IBOT, it does not train. Like, 0. You just don't get the model does not take off. Nothing works. So that's very weird. That's really weird. And finally, it flew under the radar, kind of. I mean, of course, that's very subjective, but it's not very studied. And so I think there's something to be done here. Like, you see all of that, it's got potential. It seems to go further than Dyno, but it's kind of weirdly formulated. Maybe there are some weird instabilities that should be fixed, and it's not studied enough. Well, let's study it. Studying it is studying masked image modeling. Masked image modeling, as we define it, is the concept of training a model by removing part of an image and predicting what was missing. You've got an image like this. You remove part of it, and you will want to have a model that predicts what's missing. And so there are some choices involved. First thing, well, you're going to put here some predictor, something that takes these patches as input and the missing patches and returns a prediction. And I purposefully leaving that blank because we're going to choose it together. Now, after you predict something, you're going to have to compare it to a ground truth. You're going to have to do a loss to train the model, get some gradient. And this loss, again, there's some variability on what you can do. And finally, this loss is comparing to a target, but this target has to be obtained from the original image somehow. It could be the pixels, but it could be something else, some representation of what's missing. Maybe, like, for example, if you had labels for this, you'd be interested in predicting the label dog and having a label representation instead of just pixels. But that's getting ahead of ourselves. These are the 3 main design choices that we observe. This mass image modeling thing has been already done many times. So there were many studies on this. But basically, they all take some choices around these things. And we'd like to study cleanly what do we think are the best choices and how to get the best out of it. First thing, like this might seem a bit confusing, but we'll just go about it one by one. First thing is the target representation. Now, as I was saying, you could just take the pixel values. That's the most straightforward thing to do. You've got your image, just flatten your image, and this is your target token. This is what was done by MAE and Word and also other works before and after it. MAE is a known work in SSL. If you don't know it, don't worry. But doing that focuses a lot on color and texture. If you're predicting the pixels, if you have, for example, a high frequency texture and you predict it just one pixel to the right, just shift it a bit, you're gonna get it all wrong, even though you had basically the right ID. Like if it's grass, but you don't get the right grass blades in every position, you should get a low loss. But this is gonna give you a high loss because you are trying to predict exactly the right texture. Same thing for color. If you have, I don't know, a red t-shirt and you predict an orange t-shirt, you're gonna get high loss, even though you predicted the right thing. It's a t-shirt. I mean, who knows what color it is? It does not really matter. So we would like to get something more semantic. Now, note, as I'm saying here, that this is kind of an opinion. You could disagree with me, and it's fine if you do. This is my opinion that we would like something more semantic. In practice, so far, these things do not lead to very great representations. In terms of representation learning, frozen model, it's not really comparable to very good methods. Now, something you could say is, okay, if you don't want to have pixel and you want something more semantic, let's take a pre-trained model. You take a pre-trained frozen encoder and you encode your image with this, and it gives you a semantic representation of the image. That's very nice. And it was done before. It was actually the first such work with vision transformers was called BAIT and used the latent space of a discrete VAE to do that. It did not work super well. There's also some works called EVA. They use clip models. Clip does not have super good feature maps. You could make it work, I think. I think you could make it work, but my gripe with this is more fundamental. If you were to train a good model with that, you've got your super good pipeline and you train a good model like this, the model you train hopefully will have better feature maps than the target encoder that you are using, because if it's not the case, then your model is useless. So you train a better model. But then why don't you just use this better model as the target encoder and train a new model? And you could do that again and again. And that's exactly the concept of a paper called DBOT. So small detour here. DBOT is this idea of you start with either a random or pre-trained teacher, whatever, and you train a student by predicting missing patches in terms of embeddings of this teacher. And once you've trained it, you use it as a teacher for new training. And you do that again and again. You do that, and you do that. And at some point you think, okay, if I'm just going to do that again and again, why do I not make this online? Online meaning, let's just use, for example, a delayed version of the model I'm training, just a few thousand iterations before or something. And a common way to do that in SSL is to use what we call an EMA, exponential moving average. Exponential moving average is basically a nice trick to do an averaging of weights of the previous iterations. That is kind of a delayed version of the model. It also had some weight averaging. I put good here. Basically, if you don't know it, averaging weights of different models usually is good, but nobody knows why, and it's super weird. But doing that is very hard. Every SSL method that has this feature of using an EMA is usually quite unstable. So you've got this thing of you are using your own model as target for training it, and so it could work, but it could also just find a weird local minimum and just collapse onto itself. You can have a ton of instabilities happening when you do that. It's hard. That's what makes it worthy. So let's try to make it work. As I was saying, basically, this is, the recap is you can use the direct pixels. Maybe it's a bit too low level. If you use an encoder, that should be fine, but you might as well go for the EMA, the online version. That is my opinion. You are entirely allowed to disagree, and some people, some very good researchers disagree, but I think it's a pretty natural way to do that. at least it's good enough to justify that we're going to focus our study on this EMA thing. This is the only opinionated choice we're going to make. After that, it's going to be empirical. So, second thing, how do you do the loss? Loss formulation, again, you might say, okay, why are you overthinking this? Just compare it with L2 distance, whatever, and gradient descent on that. Now, it works. It works. The reason I'm doing that is because there is this weird thing that exists in IBOT. They do an MLP projection, and the target is projected by an EMA of the MLP. It's weird. It was inspired by Dino, but I think it's basically they lost the plot, and it was justified in Dino, but here the interpretation is really unclear. I think it's a bit weird. At least if I'm trying to use it, I'm not sure what it's supposed to do, so I prefer not using it. And instead, like, what I'm gonna say is, in Dino, the justification for that was that it was kind of doing an implicit clustering. So let's go back to that. Let's step back a little and go back to clustering. And this is what we propose: doing just a clustering of the targets and predicting that, and that's all. Instead of just predicting directly the targets, you predict the cluster assignments. What's interesting is that if you do clustering of good features, for example, if you do clustering on Dino features, what you observe is that it kind of finds pseudo classes, like it kind of segments the images. So the intuition is that if we do this clustering and we predict the clustering assignment, it's kind of as if we were predicting segmentation labels, the type of object, instead of the actual pixels. And I find this very interesting. I find it much more interesting to predict if it's a dog or a cat than just the exact texture of the fur or the exact color. What I like also with that is that it's what I call debuggable. Debuggable is basically I know what it's supposed to do. I can inspect the intermediate values. I can inspect the assignments and see, do they look fine to me or not? And that's something very interesting in research, because you just, if it doesn't work and you have no idea where to start, it's very hard to improve your thing. So this is debuggable. This is kind of interpretable to me. So we're going to try that. But as I said, let's not do too many opinionated choices, and let's compare it. What is the right loss formulation? Well, the direct loss works. As I was saying, it's a fine idea. It's a fine idea, it works, but it's not that great. That's the first line. We call it IJPA because that's the way it's done in IJPA. The second thing, IBOT loss, as I was saying, it just does not take off. The accuracy is very, very low. It does not work at all. However, if we do this, so CAPI, which is our clustering proposed method, this works super well. We gain like 5.4 points on segmentation, 80-20K, and 2 points on classification. So it's really good. It seems to improve the numbers by quite a lot. So it's nice. You're going to keep it. Second choice that we mentioned is predictor architecture. Predictor architecture, what do I mean by that? Usually we use transformers, at least that's what we study. We study vision transformers. So you could just use one vision transformer. That is, you just input all of the patch tokens and you input a mask token, and at the output, you just take the output of the mask token. That is the earliest approach that was taken by like BATE, IBOT, like early works. Something that was proposed later was proposed by MAE is to split the encoding and the prediction. What do I mean by that? You've got a first vision transformer that will process only the visible patches. And that's interesting because if you are doing a high masking rate, meaning just you remove a lot of patches, then this vision transformer will forward a reduced set of patches, like only 25% of the patches, because he only forwards the visible patches. And so you are saving a lot of computation here. And after they are encoded, you feed them to a predictor, and you also feed the mask token to the predictor, and the predictor is going to do the prediction. This idea was introduced in MAE, and it was a very nice idea for like efficiency. You are saving a lot of compute by doing that. We like this, we just go one step further, saying, okay, what if we don't keep processing the patch tokens in the predictor? The predictor is just supposed to do prediction. It does not need to process the patch tokens. And so we encode with an encoder, and then the predictor just takes as input the mask tokens and gathers context information via cross-attention. So it does not process the patch tokens. This might seem like details, but honestly, in these kind of works, details are everything. Let's ablate it a bit again, and what we see is that basically Fuse works. It's a valid architecture, but splitting is better, and fully splitting by also splitting the predictor is even better. It's nice because these are just numbers, but you've got also the efficiency considerations. These are in this table. The fused model was much longer to train than the split self-attention model, which was longer to train than the last model. So this model is like the fastest, but also the best. Free lunch. That's nice. This is what it looks like if I do the same diagram as in the beginning, but replace all of the components. We have our EMA encoder, again our opinionated choice. This is the EMA of this encoder component here, and it encodes the patches of the teacher, and you get a pretty semantic patch here, but you're going to forward it through this clustering to get the clustering assignments. Hopefully these clustering assignments will be very good targets for our learning process. And the learning process is forwarded through the split encoder predictor thing. You've got just a linear layer to convert from the dimensionality of the token to dimensionality of the logits. That's basically it. Now, of course, all of this is again very just details. It's hard to justify them theoretically, so it really depends on the downstream numbers. This is very empirically driven. So let's compare it to other methods. And you've got about 1 million numbers here that you're not going to read. But follow me a bit. Here, in the first part, we compare when we pre-train on ImageNet 1K. ImageNet 1K is a pretty common pre-training dataset, relatively small by today's standards, but it's so common that you kind of have to try training on it to have fair comparisons with previous methods. The architecture, the model size, note, is not always the same. That's the annoying thing. Sometimes you can't do always fair comparisons, but we try to have similar architectures as the other models. Basically, what we see is that compared to previous masked image modeling models, we are much better, like 2 points better everywhere. We are comparable to methods that use mixed masked image modeling and other objectives, like contrastive or dino things. This is nice. Seems to close the gap with, as we were saying at the beginning, close the gap with methods similar to DynoV2. Of course, DynoV2 was not pre-trained on ImageNet 1K. It's a very big model that was pre-trained on a large dataset. And so we do this second table where we pre-train on larger datasets and we see what we can do. And although we do outperform by a lot the previous mass image models, we are not yet at DynoV2 level, to be honest. We close the gap to some extent, but not yet at the level. Classification, though, it's maybe not the best benchmark to compare on. Here we are doing really a dense objective of learning local stuff. And I think it's interesting to also look at segmentation. In segmentation, the results are similar, at least on ImageNet 1K. But then on larger datasets, you get quite good stuff. Like in some cases, you can even beat DynoV2 with our models. Like this thing on 8020K, if I pre-train my CAPI on places, I get better than DynoV2. It's not really a super good comparison because DynoV2 was not pre-trained on this dataset and it's good all around. Here, this CAPI beats DynoV2 when it's pre-trained on this dataset. It beats here on this dataset. But then on the other datasets, it's not as good. DynoV2 is still the best model all around, but you get some signal that it might be close to something. We might be approaching the idea of maybe being able to beat DynoV2 with a simpler approach. That's basically it for the results, but still want to show some pictures because we do computer vision because we like nice pictures. And these are the pictures of feature maps. How do we get these pictures? You compute the feature maps given by the model for a given image. And then you compute a PCA of these feature maps to project it to the first 3 principal components. And what you observe, and then you plot the 3 principal components in like RGB space. Just these are very rough visualization of what the model sees in its feature maps. What's nice is that it seems that CAPI feature maps are pretty semantic and smooth. What do I mean? This is not smooth, as you can see. This is not super smooth. ME is very smooth, but it's not very semantic. Look here. Actually, what you see if you look closely is that this is just dependent on color. Basically, this part here is pink because it is a shadow, so it's black, so it's dark, and so it's the same color as the trees. Whereas in CAPI, it's green because it's the same type of object. It's also a house. Same here too. The three set of legs are the same color in CAPI, but not the same color in MAE because the ones that are lighter have the same color as the mountains in the background that are white. So these things are smooth and clean representations of the pixel values, of the colors. Whereas these things seems to be smooth and clean representations of the semantics. So that's pretty nice. It looks pretty good. I mean, of course, this is very hand wavy and it's very hard to assess how good features are from visualizations, but just wanted to give you a bit of a way to read this. Thank you very much for listening. I think I'm pretty much on time. So if you have any questions, we have a bit of time for that. Thank you.
Yes. Thanks a lot, Tim. Right. So if you have questions, Lorenz, do just raise your hand and Lorenz will give you the microphone.
Hi, thank you for your presentation, for your talk. I have a question to the first paper. I read it already before, and you said that something about cosine similarity for outliers. Did you measure it for a single image or across the data set?
No, across the data sets.
So it means that all data outliers are similar across the data set.
So across the data set, outlier tokens, like outliers, appear more often on patches that are similar to their neighbors than just the
it's only about neighbors, not across, like if you take outliers from different images, they won't be the same.
No. What this means is the patch values, so like these are just blue, they are similar to the neighboring patch values, which makes sense here. You know, like this is full blue, this is going to be very high cosine similarity neighboring full blue patch.
And then another question, the vision transformer has positional encoding.
Yeah.
Does it affect the similarity between the tokens?
A bit, but positional encoding is relatively smooth. What do I mean by that? It's cosine similarity in this plot.
No, I mean in general about positional encoding. Like you add this kind of cosine thing to each token. You can't change its semantics, right?
Yeah. So just to clarify, in this plot, the cosine similarity is computed on raw pixel values. There's no positional encoding included in.
It's not between tokens. It's between pixels.
Between patches. So you take the patch that gave a token, and you take its flattened value, and you compute the cosine similarity with neighboring patches. It's just computing the similarity really in terms of pixel values.
Didn't you try like cosine similarity between tokens in the last layer, for example?
Well, in the last layer, it's going to be quite different because the patch has become an artifact.
Thank you for the great talk. I have two questions for the CAPI paper. First, I'm interested in whether you looked at the scaling behavior of that method. So do you have either a plot or an intuition about how scaling CAPI, how that works? Because as far as I can see, this is only width large, right? And how does it scale if you go larger, like if you go deeper to width G or width, like even further, or with H? And second, do you also have in comparison to the SIGLIB model? Because like Google DeepMind has shown that SIGLIB works much better than CLIP on a couple of tasks, and they just released SIGLIB version 2, which adds another thing. And downstream, that seems to be better than the CLIP, and also like both feature in terms of feature maps and downstream task performance. Yeah, those are my two questions.
So first thing was, how does it scale? We have some experiments at smaller scales to see a bit of the trend from going from ViT small to ViT large. The trend looks okay. Going larger than ViT large, let's say we kept that out of scope for future work. Tried it a bit, was not really working out of the box. I got some stability issues. So there is some stability questions that are remaining in this method. but yeah, it's future work. In terms of comparison to SIGLIP, so we don't really compare to SIGLIP, especially here, because we are doing self-supervised comparison, comparing to self-supervised methods. Same thing for SIGLIP 2, but it was not out yet anyway. Usually, so basically what I can say is that CAPI is all around not as good as DynoV2 yet. DynoV2 compares to SIGLIP differently on different benchmarks. DynoV2 has good feature maps, like for segmentation, these kind of things. On our benchmarks, like linear segmentation, SIGLIP is not really good. But SIGLIP is trained with text, and so it's really good on things like OCR. And yeah, so it's really good also for VLMs, vision language models, that are really dependent on OCR. SIGLIP 2, I don't know, it came out recently and was not, right now I am out of Meta, so I don't have compute to evaluate it, but yeah, I'm sure it's something that should be added to the baselines.
Great talk, thank you. And CAPI, how do you determine the number of clusters, manually or adaptively?
It's a hyperparameter, honestly. Beginning I was putting it to 65,000 because it's just adapted from DynoV2. In the end, it's very annoying because it's super expensive in memory, so lowered it to 16,000. 16,000 was working, maybe lower could work. Yeah, I don't know, it's something to tune.
Yeah, thank you.
Yeah, really nice talk. By dropping like the dyno loss, you basically lose this like global information token. And I mean, you had in the beginning this picture of like kind of encoding Jan into like a fixed vector representation, but then I have like a bunch of vectors. And I mean, do you see this like just from an opinion piece that we should not have this global representation during SSL, and it's just like we should learn some attentive probe and have that in the task, or do you see some way on kind of integrating to have then this global information token in the end into CAPI?
So my opinion is that just learning information in general is the hard part. Then computing a global summary of that is not too hard. What do I mean by that? For example, here the CAPI classification results I showed were with an attentive probe, as you were saying. So I train an attention layer on that. What I could do is train a self-supervised attentive probe. Like after pre-training, I freeze my model and I add an attentive pooling. And I train this attentive pooling only with a dyno loss. If I do that, I think I'm going to get basically the same results. And so this is a way to train a global descriptor out of a model that does not have any, self-supervisedly. And basically my feeling is that just training in this global descriptor is kind of solved to some very light extent. Like Dyno works super well on that. So I was more focusing on like, let's remove all of the confounding factors and focus on learning local stuff.
Yeah, thanks. And one thing with like the exponential moving average, like the nice thing in NLP is that you kind of have this perplexity, like one fixed measure where you can then like deduce scaling laws from. And like with exponential moving average, you lose it a little bit and you cannot really predict. So would that be a factor also to get rid of that in the future?
So I know people are usually used to their loss meaning something. When you get to SSL, you go through different phases of grief. You have to let go of this. Basically, I'm used to that because I've been working on Dyno so long, but the loss does not mean much. It will go down, it will go up, it will go down, up, who knows. Like the loss going up is not a bad thing. It can be the loss going up at the same time as the downstream performance going up. I agree it's a bit weird. It would be very nice to have a meaningful loss. In CAPI, we kind of get that. Don't have any proof that it's meaningful, but basically in CAPI, even though it's an EMA, after the initial bootstrapping period, you've got a kind of bump at the beginning. After that, it's really smooth going down and just always going down. And I did some plots which I did not include in the final paper of like trying to find correlation between loss and downstream scores. And I could find a very, very nice anti-correlation, like lower loss means higher downstream scores. So maybe CAPI could bring that, but there's no guarantee here.
Oh, that's nice to hear, yeah.
Okay, Lucas had another question? Okay.
Yeah, just following up on this, because I thought about this too, like partitioning local and global information into pre-training, post-training phases. Is this essentially what your gut feeling is too, that we could disentangle like learning global information about our space from local information by like just saying, okay, in the pre-training phase, we focus more on like learning like from statistics of our data about local information, local similarity spaces, and then freeze that model, or say we can just add a regularization during pre-training that regularizes our post-train fine-tuned model towards like the initial starting point, like the convergence point of the pre-trained model, to not move too far away from that. By adding, like as you mentioned, but we could replace the dyno loss by something else that just adds some global information in a second phase. Either we call it mid-training or post-training, but I wouldn't call it fine-tuning because there's no target task. Essentially, it just wants to add like this classification token info that we've had during the dyno loss. Like, is this what you? Because in my feeling, that could be the case. Like, there's evidence for like partitioning this into 2 training phases.
Yeah, so I think it's I think it's something that makes sense. What I was more pushing towards is not even fine-tuning the whole weights, just freezing the weights and adding a last layer for pooling. But
I see, like an attention probe or something.
Yeah, exactly.
Yeah. Okay.
Both are fine to me. Yeah, makes sense.
Okay, thank you very much for your nice questions and the great answers. And generally, let's thank Tim again for the nice talk.